as Neil says, I really am not quite sure how I'm going to follow that. We probably share a similar vein of thought towards accountants, but my presentation was probably slightly kinder to that. And I was quite pleased to hear that it was probably only Neil here that appreciates under that guide. So we're going to stick the knife in as well as we go through the presentation. And there's a lot of similarities from what's being said in the previous presentations to what we're going to talk about now. So it is about the total cost of ownership. It's about when to repair or to replace an electric motor and what effect that has on the energy savings and also on the carbon emission reductions. So you've seen these slides before. You're going to be sick of pie charts by the end of the day, I'm sure, and bar graphs, but the message is very similar from a supplier point of view and from an end user point of view. So in the UK in total, you're looking at sort of 328 terawatt hours. You can see there that domestically about 37% usage, and electric motors within the total UK consumption attributes to around about 20%. And if we take a look now at the UK industrial consumption, then they're taking just under a third of the total usage, and as you can see there, a whopping 65% of that usage is directly attributed to an electric motor. So they are a huge consumer of electricity, consequently a huge cost to your businesses. Again, we can all supply you a motor for a fiver cheaper than the next man, but the important thing is that the actual cost of that electric motor attributes to 97% of its purchase value. So it's the energy that it's consuming is the all-important thing to consider, not the purchase cost. So, running costs, you see lots of graphs and presentations of terawatt bits and gigajoule that. But when I open my electricity bill, I'm not interested in how many units I've used. I don't tell what, my goodness, you've used 10 terawatts of this today. I want to know what that bill is at the bottom. How much am I exactly paying? So how much do electric motors cost to run? Well, it's a recognised saying that a motor will easily exceed its purchase cost within a month. So if you've got a £50 motor, within a month it's going to spend 50 quid. If you spend £5 within a month, it's going to cost you £5 to run it. It's very expensive indeed. So some typical running costs here: a small 1.5 kilowatt motor could cost you around about 25 quid a week to run. A standard 4 kilowatt motor, 270. Getting a little bit bigger now, 37 kilowatt motor, which is not a massive motor in your industry, £28,000 a year to run. And if you've got a nice chunky monkey, you've got a 132 kilowatt motor, then over an estimated 15-year working life, probably including a couple of rewinds along the way, that's going to cost you almost £2 million. So these motors cost an absolute fortune, and when you accumulate them all together, what you've got on site, they are a huge expense to your businesses. Again, we talk about carbon dioxide and CO2. What is a tonne of CO2? We can't see it, we can't smell it. Well, a tonne equates to around about 1800 kilowatt hours. That equates to a small 2.2 kilowatt motor running for just over a month, 24/7. That 2.2 kilowatt motor running for a year is going to generate just over 19,000 kilowatt hours, which equates to 10 tonnes. So it's just giving you an idea of the sort of emissions that an electric motor throws out and how it translates into a CO2. Again, I'm going to hold no apologies for showing this slide. You've all heard about the CCLs and the EUGSs. The reason we use this slide is that you look at that first there, way back in 2001 we were talking to customers about using high efficiency products. And it's only sort of now that policies are starting to kick in where people are starting to specify high efficiency products such as electric motors and such as inverters. There's a whole host of taxations there, and they're even starting to mop up the rest of us, building users, company like ourselves, who would quite easily exceed £500,000 in energy, so they're mopping everybody up. So what were they doing? Well, to combat the efficiencies, and back in '98 there was a low voltage efficiency labelling scheme. You'll have all seen these labelling schemes now. They started at the very low efficiencies at EFF3, moving into EFF2, and then high efficiency motors at EFF1. And it covered a range of electric motors from 1.1 to 90 kilowatts in 2 and 4 pole. So then there was a global standard put together for motor efficiency. So it was about defining the energy classes for the three-phase electric motors. But then there was a standard introduced which would determine the losses in efficiency. Prior to that, motor manufacturers were declaring their efficiencies, but there was no real governing body that was saying, how are you actually telling us what this efficiency is? So this standard now means that all the major, or all the motor manufacturers have to declare their efficiencies to a given standard. So it was introduced, now an international code, and then just to confuse us all, they decided to face all the efficiency schemes. So the lowest efficiency motor is IE1, and then progressing to IE2 and IE3. And IE4 is a technology that they're yet to determine what efficiency schemes will be available, but the product is starting to come through now from the manufacturers. So that is just to give you a comparison of where we are. The old EFF1 scheme is now equivalent to the IE2, and it covers all motors right down from 0.75 up to 375 kilowatts in 2, 4 and 6 pole. So just to give you an idea of what those efficiency improvements mean. So in the old standard, you've got the efficiencies on the left. So moving from the old EFF2 or IE1s is now into the IE2. So a small motor would be giving you a 7.5% improvement, and a large machine about 1.2. Moving into the next level to the IE3 standard motor, you'll see that that motor is now about 10.4% improvement, and the bigger motor 2.1. So the message that we're saying here is that you've got lots of small motors, there's some big improvements to be made, and you've got relatively fewer, although the percentages are smaller, and the savings are still significant. So then there's now some directives regarding the actual production of these machines. So the eco-design legislation was set in, and use of VSDs with high efficiency motors as well. And as of June of last year, then the bare minimum of efficiencies that could be supplied into the UK was IE2 from 0.75 kilowatts to 375 kilowatts. And as of January 2015, the minimum will be IE3 from 7.5 to 375, or an old IE2 with a variable speed drive, and then moving into 2017, then it'll be right the way down to 0.75. So that's where the legislations are moving towards. So then we saw the enhanced capital allowance lists before. Well, they've now changed the goalposts on that, because motors now, you can only qualify for the ECA on electric motors that are in as IE3. So although they've now told you IE2 is a standard, you're not going to get any money unless you put an IE3 motor in. So they're moving the goalposts all the time. So, how can an electric motor help you in reducing savings and reducing carbon emissions? It's about when you repair or you replace, and this is where we come into our accountants and our engineers. So it needs to be a decision that's really based on fact. You should be replacing motors with the highest efficiency products available, and the repair-replace philosophy should be built around the total life cost cycle. So there's calculators available in our industry as well. They're pretty much all web-based. It offers an unbiased recommendation to what you do with that electric motor. The results are based on current conditions and life cycle costs, and it gives clear comparisons between the repair and the replace option. So there's some data that you put into there. So you just put in there your powers, speeds, frame sizes, etc. The old efficiency band of that motor, how many hours is it running for? Most motors, we reckon, run around about 3/4 load. You may have a bit of history regarding that motor, so you know that it's burnt out once before, and you reckon that you would get a life cycle of 5 years. So you're banging your criteria, and the selector is saying, right, we believe an IE3 motor is the best choice of selection for this particular application. And the reason for that is that if you repaired it, you're looking at 1,500 quid. These are the sort of same, I'm not going to read them all out. But if you enter an IE3, you're going to be spending more than double the price to repair it. but over a 5-year life cycle, then you're comparing about £6,000 saving. So this is where the bean counters now are talking. So the engineer likes the idea of this because that's what's best for his plant, but the bean counter likes the idea of that. So this is where there's a balance between the two and what is best for the company. Is it best that I save my money now, or am I planning for the future and looking for the best deal that I can possibly get? We also recognise that a lot of these motors are old, so in that selection process, the calculator can then produce a sheet which gives you the dimensional differences. Some of your motors might be imperial, so it gives you an idea of what work might be involved to change from an old style motor into a newer style motor. So the sustainability part, a bit like your good sales, when you already mentioned, you don't want to be trucking clay all around the country. We don't want to be trucking motors around the country. So the plan would be that you would have a review on site. The TCO calculator would tell you whether it's best to repair or replace it. That replacement could be via some consignment stock or stock that you've got already on site. Any irreparable assets can be stored for an en masse collection by any registered recycling organisation that you may use. So again, we're not transporting electric motors from a place of work to a repair shop, from a repair shop back to a place of work. And we believe that we can reduce carbon footprints. We just won a contract with Tata Steel, and we reckon transportation alone would save them £100,000 in transportation costs through their CO2 goals. But you also benefit yourselves from the financial benefits of having that electric motor to recycle yourselves rather than the repairer or the rewinder who's got it. Not forgetting that there's huge energy savings via using inverters with motors. So obviously fans and pumps are the key areas, centrifugal fans and pumps. Fluid power is a function of flow and pressure, so flow is proportional to your speed, so where you get the cube laws from, pressure proportional to speed squared, and power is speed cubed. And what all that means is that basically if you can slow your motor down from 50 Hz to 40 Hz, then you're going to save half the power consumed by that electric motor. You need to understand how that's going to affect the process, what you do, but these are the real benefits that can be achieved by fitting inverters. So why inverters? Well, they're constantly monitoring the motor, protecting it. It's providing soft starts for the motor and any connected equipment to it. They can stop more motors quickly as well, making machines safer. But they can also optimise the electricity to that electric motor so you're getting the best performance and producing the cost savings. So again, for most machines slowing down by 10%, you'll lose 10% power. But if you've got lots of rooms full of pumps or lots of rooms full of fans, and some big savings that can be achieved. So in summary, the total cost of ownership, it's about the product that you're actually replacing. It's about the application as well. You need to make sure that the hours running is applicable to putting high efficiency motors in. The life cycle costs should definitely be considered. The availability. Now if an IE3 or an IE4 motor is not available, you're not going to have a machine stood still. You're going to replace it with the highest efficiency product available. The technical benefits of fitting inverters onto plant. Can we do that? Is it applicable to these particular applications? And the legislations will also help in choosing what products you move forward, but again, cost and budget will have an effect on what motors you choose to go for.